Today I'll be attempting the final problem from the 2014 Maths Extension 2 HSC exam. So we've got an integral of indefinite integral of log x divided by 1 plus log x all squared dx. Okay. So for this question we've got a fraction with a numerator and a denominator. So numerator log x and denominator 1 plus log x squared. So in these types of questions involving fractions, we can attempt doing integration by parts. So here, what's our u and v going to be if we use integration by parts? What we could try is first writing v, and you want the derivative of v to almost appear here. And let's try making the derivative of v appearing in the denominator, so 1 plus log x squared. What I'll try is v equals 1 plus log x. This means the derivative of v is going to be, we use the chain rule, so derivative of the log x is 1 over x, and derivative of the 1 over stuff, we'll have negative 1 over 1 plus log x squared. So that's negative 1 over x times 1 plus log x squared. Okay, now we want to set u, so uv dash is equal to this. So u must equal negative x log x. And this is in order for u times v dash to equal the ln x divided by 1 plus log x squared. Okay, so now by setting our u and v values, we can now use integration by parts. So the integral of ln x over 1 plus log x squared dx is equal to uv minus vu dash dx. This is equal to minus x log x, and v is equal to, we have divide by 1 plus log x, and now we minus, so we're minusing v, which is 1 plus 1 over log x, and our u dash is equal to oh yeah, we haven't found u dash yet, so we'll find u dash, which is using the product rule. So our derivative of x is just 1, so we have negative ln x minus, and now we have x, and derivative of log is 1 over x, so we have minus log x minus 1. So u dash will be minus 1 minus log x dx, and this is minus x log x divided by 1 plus log x. This stuff over here is equal to minus 1. So we have minus dx, and we have minus x log x plus 1 plus ln x. And this will give us plus, so the two minuses become a plus, and it just becomes plus x here, and plus c. And now we have minus x log x, and now bring this all under one fraction, so we have plus x times 1 plus x log x divided by 1 plus log x plus c. So now we have the x log x's cancelling out, and we have x over 1 plus log x plus c is our final answer. Okay. So this solution uses integration by parts. So here I've chosen v first, and then by finding v, I've made v dash as close as possible to this original expression, and then I chose u to make u times v dash equal to the expression inside the integral. And I'll show you a second way of solving it, and this is, you can observe the denominator of the fraction is something squared. And this is actually quite similar to using the quotient rule in derivatives. When you find derivative of f of x over g of x, the denominator is g of x squared. So you can actually use a similar line of reasoning and try to reverse engineer what the original expression was, where if you differentiate it, you get this ln x over 1 plus ln x squared. Okay, so for example, if I have the function f of x divided by 1 plus ln x squared, just not squared, just 1 and 1 plus ln x, and now I find a derivative of this expression. Will be using quotient rule. F dash of x times 1 plus ln x minus f of x, and derivative of the denominator is 1 over x. And now you're dividing by 1 plus ln x squared. Now we want this to equal ln x over 1 plus ln x squared. Okay, so we can see there is an x divided by x in the denominator, but no dividing by x in the numerator. There's no dividing by x here, which means we might expect the x's to cancel out. So let's try putting if we try putting x over here for f of x, then derivative of x is 1. So if we try it out, this expression ends up being 1 plus ln x minus 1 divided by 1 plus ln x squared. And this is equal to ln x divided by 1 plus ln x squared. And this is the correct expression that was in the original integral, which means if you put f of x equals x, you'll have x over 1 plus ln x. And it proves this is a valid antiderivative of the original expression, which means you can just do plus c to get the answer to the final integral. Okay, so that's 2 different ways of solving this final problem from the HSC. So you can either use integration by parts by finding v first and trying to differentiate it to get as close to the original expression, or trying to spot a pattern that involves the quotient rule to try to reverse engineer the integral. Okay, that's all I have for you today. Thanks for watching, and I'll see you next time.